Chapter 3.1, Quadratic Functions in Vertex Form. Essential question, what does the vertex form of a quadratic function reveal about the function? 1. Location of the vertex. And that should be kind of obvious. Okay, now 2. Does parabola, which is the shape of a graph of quadratic function, open up or down? So really, it's going to be to answer this question. Does the parabola open up or down? And finally, the width or narrowness of the parabola. I'll just put down of parabola. Okay, let's go ahead and look at what we have here. Here we have teach. Transform a quadratic function fx equals ax squared plus bx plus c to the form fx equals a times quantity x minus h squared plus k. And what we have here is a controls up or down, and I'll just say narrowness of parabola. You could call it width. Okay, this h here is x minus h. This affects the horizontal position of vertex. And what does k affect here? K is going to affect what? What do you think? Vertical position of vertex. And this form here is quite familiar to what we went through when we looked at chapter 2, which was for absolute value functions. Same format, an A, an H, and a K. Next, investigating attributes of a quadratic function in vertex form. And I already explained on the prior page really what that was. The vertex of a graph is located at the coordinate pair h, k. So if we can find what h and k are, we can find the location of the vertex. And also we have here, remember that when h is greater than 0, the graph of fx equals ax squared opens upward. So the graph of g of x equals negative ax squared, which is a reflection of fx in the x-axis, opens downward. And so upward when a is greater than 0, and downward when a is less than 0. So that's one of the 3 things that the vertex form is going to tell us. So we have a couple examples here of graphs. And here we have A, and this one on the left is equal to, says 0.5. We'll put it in fraction form, 1/2. And we have here H is equal to -1. And then lastly, we have K is equal to -3. So the location of our vertex here is the coordinate pair -1, -3. Okay, which is what we have here. Now, one thing, if we continue to the right here and we take what is x minus -1? So I'm going to rewrite 0.5 as 1/2. Well, that's going to be x plus 1. And we have squared minus 3. And so the takeaway here is if you see in your parentheses here a plus something, that means that h is going to have to be negative for that to occur. Now let's look at this parabola on the right. We have a is equal to -2. Well, that means that the negative sign means we're turning it upside down, and this 2 here is going to stretch parabola by factor of 2. Now we have h is -2, h is 2. H equals 2. We have k equals 4. So we have our vertex here at h comma k equals 2 comma 4. So we are going down from the vertex, opening downward for our parabola. So we can see, I hope, the contrast between these two parabolas. The one on the left, we have an h value of 1/2, which widens the parabola, and we could say compresses, vertically compress by factor of 1/2. And this one on the right will vertically stretch by a factor of 2. Let's go on here. Identifying the attributes of a quadratic function in vertex form. And here we have our, when a is greater than 0, f of x has a minimum value of k when x, when or where, this is where, you can say alternatively instead of when, x equals h. And so we have set notation, domain of the function of f of x, and we have in other places written this as, we can put x such that x is greater than -infinity, but less than infinity. So that's another way of writing this. This thing here reads, the domain of f of x is x such that x is an element, so that little sideways e element of all real numbers. And the range is going to be y such that y is greater than or equal to k. So k is our lower boundary here. And so our range is going to go up from k. So y is going to be greater than or equal to k. And then for end behavior, we say f of x is decreasing from, it's not end behavior really, that the intervals decreasing from x is greater than -infinity to h and increasing on the interval from h to positive infinity. And then for a downwards opening parabola, very similar, except that your domain for quadratic functions is always going to be this. Always. But your range is going to depend on having a maximum or minimum value. Here we have a maximum value of k, and so y is going to be less than or equal to k, or the range. And in interval notation, we would write that as -infinity to k. That's what our range would look like. And the interval notation here, our domain is going to be negative infinity, comma, infinity. And back here on this other one, our range in interval notation is going to be, with k at the minimum, we bracket k first, comma, infinity. And our domain is going to be interval notation negative infinity, comma, infinity. Okay, let's go on here. And we have f of x is increasing from negative infinity to h, and decreasing from h to positive infinity. So increasing all the way up to x equals h, and decreasing all the way after x equals h. Okay, here we have example 1. Identify the axis symmetry on the graph of the function, then give the function's maximum or minimum value, domain range, and the intervals for the functions increasing or decreasing. So this gives us all of what we've seen before. We have our a value here. We have h is equal to 3. We have k is equal to 4. So our vertex location is going to be the point let's say that vertex is going to be the point h comma k, or 3 comma 4. And our axis of symmetry is going to be x equals h, and that's going to be the same as the first value in the coordinate pair, so x equals 3. Now, the axis of symmetry is not 3, it's x equals 3. Okay, since a is greater than 0, f of x has a minimum value of k, or 5. So we're going to be going upward from the y value of 5. And we have a domain and range, all this in set notation. And then decreasing on our interval notation. So decreasing from x is greater than negative infinity to 3. Increasing from h to positive infinity. So let's go ahead. And we have some blanks to fill in here, similar to the last one. So we have our quadratic function in vertex form with an a here, with an h here, and in this case h is going to be negative 5, and k is going to be equal to negative 1.6. So to get this x plus 5, we have to have x minus negative 5, and then plus, we have negative 1.6. We'll just fill in the blanks. So a is equal to negative 11, h is equal to negative 5, and k is equal to negative 1.6. Axis symmetry, x equals h. So x is equal to negative 5. Since a is less than 0, f of x has a maximum value of k, or negative 1.6. That's our value of k. Domain x such that x is an element of all real numbers. Range y such that y, in this case we're opening downward with k, with a being negative. So y is going to be less than or equal to k. So y is less than or equal to negative 1.6. And the last line here, increasing on negative infinity to 8. So increasing on negative infinity to negative 5, decreasing on h to positive infinity, so decreasing on greater than negative 5. to positive infinity. Your turn. Identify the axis of symmetry, then give the functions maximum or minimum value, domain range, and intervals where the functions increase or decreasing. Well, let's identify A. A is equal to -1. H is equal to 0.8. And K is equal to, well, we don't see anything, so K is equal to 0. What that means for this quadratic function is our vertex is going to be the point h comma k, so we have 0.8 comma 0. That will be the location of our vertex. So our axis of symmetry, abbreviate AOS, is going to be x equals 0.8. That's our axis of symmetry. Function's maximum value. Well, we are opening downward, and so our maximum value is going to be k. So maximum value equals k, which equals 0. Domain. And I'm going to use the same notation we've seen earlier. X such that X is an element of all real numbers. That fancy script looking R. And in interval notation, we would say greater than -infinity to less than infinity. Okay, that's going to be interval notation. Range. Let's look at range. We're going to be having a maximum value of 0, so we're going to be going from -infinity to less than up to 0. And that's an interval notation. Let me go ahead and put that instead in set notation for consistency's sake. So we're going to have range y such that y is less than or equal to 0. And then, of course, in interval notation, we would put open parentheses, -infinity, 0, like that. And increasing and decreasing. So increasing on the interval from -infinity to h, and h is 0.8, and decreasing once we get to the maximum on h, x equals 0.8 to less than positive infinity. So that covers it all here. I invite the viewer to go ahead and work on 6 after pausing the video, and then play ahead to see if you got it right. Okay, number 6, we have axis symmetry. Well, the vertex is going to be, h is going to have to be equal to -1. So vertex is -1, comma 1. Our axis symmetry is going to be the equation x equals h. So we have x equals -1. Maximum, do we have a maximum or minimum value? Here we have a is greater than 0. So k is a minimum value. And so minimum of 1, right? Okay, I'll put k equals 1. That's our minimum value. Let me just articulate that a little differently. I'll say minimum value is equal to k, which is equal to 1. Okay, domain. Well, domain is going to be the same as we've seen previously. Domain, we have set notation x such that x is an element of all real numbers, and we're going to have actually that's going to be bracketized there. There we go. I'll change that to bracket. And then also in interval notation, we would also put greater than negative infinity, so less than infinity. Range, we have y such that y is greater than or equal to k, and k is 1. And also in interval notation, we could write this as greater than or equal to 1, less than infinity. And then increasing on from the minimum. So we're going to increase from our value of h, which is from h equals -1 to less than infinity, and decreasing on greater than negative infinity to less than -1. So that will be that. Converting from standard form to vertex form. And we have a discussion here about completing the square, perfect square trinomials. And I'm going to try to give an example of this. If we have, say, a quadratic expression, x squared minus 6x plus 7, how can we convert this expression into a perfect square trinomial? Well, literally, what is happening here in completing the square, it's like we have a big x squared here, and we call this an x squared. Then we have negative 3x on each side. So we have that on one side here. Okay, so we have that. So we're going to have minus 3 here, minus 3 here, and these are going to be 3 x's. Well, completing the square, we're going to have numbers inside this square here. So this is what that's going to look like. How many squares do we have here? Perfectly made, of course. We're going to have 9. So to complete the square, have a perfect square, we would need to take this x squared minus 6x plus 9, and then over here we put plus 7. And since we added 9 to get our perfect square, what do we have to do outside? Subtract the 9. And so we can rewrite this expression as a perfect square. So we would have 20x minus 3 squared, because if we expand this 20x minus 3 squared, we would get this x squared minus 6x plus 9. On the outside, what we have left is going to be negative 9 plus 7. So we can put minus 2 out here. And so this expression here that I'm circling is equivalent to this expression in standard form that I'm arrowing off to. They are equivalent expressions. When we complete the square, we're going to turn this standard form into vertex form, from which we can more easily graph our quadratic function. So we have a step process here talking about what to do. It's kind of an academic way of doing it. We're just going to work ahead on this. We have an example of creating a square here, perfect square. So we have this, we factored out this 2 from this 2x squared and 12x. You get 2 times 20x squared plus 6x. And so what do we have to add in here? Well, we have to take that 6, divide it by 2, that middle term coefficient, and get 3. And with that 3, what do we have to do to that? We have to square it to get 9. So we have to add 9 out here. But we got to be careful because we added 9 here, but it's going to be 2 times 9, which over here is going to be minus 18. And which is going to be this 6 over 2 squared. So what that's going to give us is this part here becomes our perfect square, and then this 10 minus 18 becomes on the outside our negative 8. And so now at the very last we describe what the minimum value is and so forth. And then we have another example problem here, which I'm not going to go into out of interest time. Now your turn. Write the quadratic function in vertex form by completing the square and identify the maximum minimum value of the function and value of x at which it occurs. I pause the video here, let you go ahead at that, then play ahead to see if you got it right. Okay, the first thing I'm going to do here is let it be in terms of x squared. So if we factor out a negative 2 from this negative 2x squared, we have x squared. And if we factor out a negative 2 from this negative 8x, we're going to have plus 4x. And then we're going to add something in here that we don't know what it is yet. And then we're going to have way over here at the edge, I put plus 3. So now what are we going to have to put in for our perfect square? Well, we're going to have to take our coefficient of 4, divide that coefficient by 2, which will equal 2. And we're going to take that coefficient squared, which is 4. So 4 is going to go here to make our perfect square. And now we have to see what else we have to add to the outside to balance. Well, on the outside we have negative 2 times 4, so we're subtracting 8 by virtue of putting this 4 in here. So to keep things balanced, we're going to have to add 8 on the outside. Okay? So what we're going to get is f of x equals negative 2 times quantity x plus 2 squared, and then on the outside we have this plus 8 plus 3, which is going to be plus 11. And so we have a is equal to negative 2, h, since we have x plus 2, h is going to be equal to negative 2, because x minus negative 2 is x plus 2, and finally k is equal to 11. So now identify the maximum minimum value. So we are opening downward, so we will say we're going to have a maximum value of 11. And that's going to occur where x is equal to -2, which is our vertex. And so that explains the minimum maximum value function and the value of x at which it occurs. So that's it. I will just add we have a vertex at the point h comma k. So we're going to have -2 comma 11. That's going to be the location of our vertex. Opens downward, vertically stretched by a factor of 2. So that's it. I hope this has been helpful to you as an introduction, and thanks for viewing.